Find the displacement at point F in millimeters. In this problem, a 90 kilonewton point load acts vertically downward on the rigid beam AB. The rigid beam is supported by column AC, which is composed of steel, and by column BD, which is composed of aluminum. The lengths of the rigid beam and columns are provided. Since the 90 kilonewton load acts vertically downward, the displacement at point F will also be downward. And since beam AB is rigid, the deflection at point F will be a linear combination of the change in lengths in columns AC and BD, where alpha ranges from 0 to 1. If point F coincided with point A, then alpha would equal 1, and delta F would equal delta AC. If point F coincided with point B, then alpha would equal 0, and delta F would equal delta BD. Therefore, alpha equals the distance from point F to point B divided by the distance from point A to point B. After plugging in these lengths, alpha calculates to 0.667. Using 0.667 for alpha, delta F equals 0.667 times delta AC plus 0.333 times delta BD. Next, we have to determine the change in length, or axial deformation, in the two columns. The axial deformation in a column, delta, equals the axial force in the column, P, times the length of the column, L, divided by the modulus of elasticity of the column, E, and the cross-sectional area of the column, A. Since the forces, lengths, elastic moduli, and areas may not be the same for both columns, we'll evaluate the axial deformation of each column individually. From the problem statement, we've been given the elastic moduli of each material as well as the column length. But we still need to calculate the axial force and the cross-sectional area of each column. From statics, we can determine the axial force in each column by summing the moments about point C and setting the quantity equal to 0. The axial force in column BD equals 30 kilonewtons. To find the axial force in column AC, we can sum the forces in the vertical direction, set that value equal to 0, plug in 30 kilonewtons for the axial force in column BD, and calculate the axial force in column AC to equal 60 kilonewtons. Since both columns are in compression, the displacement delta F will be in the downward direction, as depicted in this figure and as mentioned previously. The cross-sectional area can be calculated from the given diameters for each column, where the area equals pi divided by 4 times the diameter squared. Plugging the two diameters into the equation, the area of column AC equals 314.2 millimeters squared, and the area in column BD equals 1,257 millimeters squared. With all the parameters in the two deflection equations determined, we can plug in the appropriate values and multiply by a conversion factor. and the deflections in columns AC and BD equal 0.286 millimeters and 0.102 millimeters, respectively. Substituting in the axial deformation for the two columns into the previous equation, the displacement at point F calculates to be 0.225 millimeters. When reviewing the possible solutions, the answer is B.